Hello, ladies and gentlemen. Sorry I missed you today, but we're going to finish off solving exponential equations. This is in your workbook, page 125, and this will serve as your lesson for this. And then you'll do the extra practice. That's also in your workbook, and we will move on from here next day. So solving exponential equations is what we're going to be talking about. And I've got 3 different points here, and then we jump right into examples. So in exponential equations, the variables appear as exponents. And here's an example. So this is an equation. We have a left side, we have a right side, we have an equal sign, which gives us that equation idea, and we have our variable is in the exponent. So your exponent equals a variable. That gives you a exponential equation. Okay? And as we know with equations, what we usually do with equations is try to solve for them. We try to solve for the unknown. So when we're working with this, we're going to be trying to figure out what x is going to equal. Now let's stay on this question just for a minute. That is 5 to the x equals 25. So it's a question. It's saying you, hey, 5 to the x equals 25. What must x equal? And I think we can tell. We know that 5 times 5 is 25, so we can easily tell that x must equal 2 just by inspection. So we know that 5 squared equals 25, and it's very true. So what that means is that in this case, 5 to the x equals 25, and 5 squared equals 25. So if I was to think about this a little bit differently, 5 to the x, 25, if I thought about the 25, I know that 25 is the same as 5 squared. So now look at this equation. If I get rid of the 25 in the middle, if I come up with this, so 5 to the x equals 5 squared, and remember 5 squared is 25, notice the bases are the same. So 5 to the x must equal 5 to the 2, which means that if the bases are the same, then the exponents must be the same. And that's our logic here. So what we're going to say is that if I have an exponent, a to the x, and if it equals a to the y, so notice your bases are the same. So if I have an equation where the bases are the same and they're equal, then it serves us to understand that x must equal y. And that's a therefore statement. So it's a logic statement, okay? It's not really a mathematical operation. It's a statement that says, well, the bases are the same. They're equal to each other. Both the left-hand side and the right-hand side are equal to each other, which means that these exponents must be equal. And that's a truism. And it's true for all the numbers except for 3 of them. So here it is here. If a to the x equals a to the y, then x must equal y. And it's true except if a equals -1, 0, or 1. Now the reason for that is, let's take a look at 1. If I have 1 to the 3, it also equals 1 to the 5. It also equals 1 to the 7. It also equals 1 to the 100. All of these equal 1, because no matter how many times you multiply 1 by itself, you're still going to get 1. So we could have some weird looking equations here. That's a true statement. 1 to the 3 equals 1 to the 5. Why? Because they both equal 1. Well, the same thing's going to happen to 0. 0 to the 5 equals 0 to the 7. Why? Because 0 times 0 times it just equals 0. And the same thing's going to happen with -1. Now, it's not as easy. -1 squared will equal -1 to the 4, okay? But -1 squared would not equal -1 to the 3. So it does matter, because this is going to be a negative times a negative. The end result is a positive. This one's going to be a negative times negative times negative. The end result is going to be a negative. But we do know that as long as I keep this even, it wouldn't matter what exponent I gave it. They're all going to work out to be positive. And as long as I kept this odd, they're all going to work out to be -1. And so it does not follow that if a to the x equals a to the y, that x equals y. If it does not follow, if a is -1, that won't hold true. Sorry. If a equals 0, that won't hold true. And if a equals 1, that won't hold true. But for any other basis, it will hold true. These are your only exceptions. So, number 3, in words, if the bases are the same and the left-hand side equals the right-hand side, then the exponents must also equal, as long as the base is not -1, 0, or 1. So, let's jump in and do some examples. 3 to the x equals 3 to the 6. Notice that the bases are the same. Notice that we have an equality here. Let me zoom in a little bit. So what we have here is, therefore, x must equal 6. And that's all there is to it, people. That's it. 2 to the x equals 2 to the 10. Therefore, x equals 10. Oh, I can put a polynomial or an expression. X minus 3 equals 6 to the 4. Therefore, x minus 3 must equal 4, so it's not a big deal. All I did is change it from being a singular number to an expression, and then we would simplify this, of course, solving for x. And notice that's what you're doing. You're solving for x. You're isolating for the variable. So now I have 2 expressions in top. Notice that my bases are the same. I have an equality here, so it's x minus 4 equals 3x minus 7. Rearranging this, I would bring the x over to keep my, well, I don't know, maybe I'll bring my 3x over. So it'll be x minus 3x, which is negative 2x. Bring this over, it's going to be negative 7 plus 4, so that's negative 3. So it's going to be x equals negative 3 divided by negative 2, which is 3 over 2. Okay, so we can get answers that are fractions. Don't be afraid of that. This one we've done already, but notice that they haven't written this with a base. They haven't made this a nice base yet. So if it's 5 to the x, if I can change this to base, same base as this one, so if I can change the 25 to the same base that I have here, then I can use my little trick that the bases are the same, I have an equality, therefore the exponents must equal each other. I'm going to use the same idea here. So we want to change this to base 3. So 81 needs to be changed to base 3. So I know it's got to be base 3, so it's 3 times 3 is 9, times 3 is 27, times 3 is 81. So it's 3 to the x equals 3 to the 4. Therefore, x equals 4. Nothing to it. Let's take a look at the ones down here. My base is negative 2, so I want to change 32 to a base of negative 2. So it's going to be negative 2 to the x equals negative 2. Now I got to think about this. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2. So it's to the 5. And notice it's to the 5, so it's going to be negative times negative, times negative, times negative, times negative. 5 negatives, that's going to give me a negative end result. So the bases are the same. Therefore, x equals 5 in this case. Looking over here, we've got this 49. We're going to want to change it to a base 7. So it's 7 squared, and therefore x minus 2 equals 2. X equals 4. And the last one on this side, so looking at this, we're going to want to change this to base 4. So it's going to be 4, 3 to the x. How did I know base 4? Because that's the base that I'm working with here. So it's going to have to go to 4. 4 times 4 is 16, times 4 is 64, so that's 4 to the 3. Therefore, 3x equals 3. Therefore, x equals 3 divided by 3, which is 1. Okay, flipping this page over. Now we're going to see some more interesting ways that we can do this. Look what we have here. We have 2 to the x and we have 4 to the x minus 1. The bases are not the same. Remember, your bases must be the same. These are not the same. Can I change them? Can I change both of them? Can I change just one of them? This 4, recall, 4 is the same as 2 squared. So what I can do is replace this 4 here. Now that's 2 to the x, that just came down. But I replaced that 4 with 2 squared x minus 1. So instead of the 4, I wrote 2 squared. Now notice that this is 2 squared to the x minus 1. So that's going to be 2 2x minus 2. Now you be careful with that. I'm going to start yelling at people when they goof this up. They're going to forget to take that 2 not only to the x but to the 1. There's going to be trouble when that happens. So what you have now is therefore the bases are the same. So x must equal 2x minus 2. I'm going to bring the x over here and the 2 over here. So 2 equals 2x minus x, which is x. So therefore x equals 2. Okay? And you can do that in different order and rearranging if you want. That's the way I'm going to do it though. Okay, so here we have 16 and 8. So we want to change the 16 to 8 something, right? Well, it doesn't work. 16 does not go into base 8. If you try to do 8 squared, that's 64. It's not 16. So no go. Watch out for that. I cannot change this to base 8. I could change it to base 4. That would be 4 squared. But I can't change 8 to base 4. So 4 squared is not 8. It's 16. So that doesn't work either. So I have to find a common base that they can both be changed to. 16 can be changed to base 2 to the 4. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's a good one. I can use that one. And 8 can be changed to base 2. 2 to the 3. 2 times 2 is 4, times 2 is 8. So that one can be used. So the 16 that I have is going to be changed to 2 to the 4. So 2 to the 4, and it sticks with the 2x on the outside, because all I did was change the 16. The 8 becomes 2 to the 3 with another 3x, because all I did was replace the 8 with 2 to the 3. So now it's got to be 2 to the 8x equals 2 to the 9x. And what you get is therefore 8x equals 9x. And what you get is 0 equals 9x minus 8x. I took it over to the other side. And what you get is x equals 0. So the only value that will allow these two to equal each other is x equals 0. All right, I hope you're getting the hang of it. Let's take a look at the next one. So I've got 9 and 27. I can't change 27 into base 9. So I'm looking for a common base. I'm looking at a common base of 3. So 9 is equal to 3 squared, and 27 is equal to 3 to the 3. So I'm going to replace them. The 9 squared becomes 3 squared. The 9 squared. The 9 becomes 3 squared, x plus 1. The 27 becomes 3 to the 3 to the 2x. I now expand this. It's 3, 2x plus 2 equals 3, 6x. Notice that the bases are the same. There's an equality sign, so therefore 2x plus 2 must equal 6x. Bring this over to the other side. I get 2 equals 4x. Divide both sides. I get 2 divided by 4 equals x. X equals 1/2. And the last one that I need to do before you've got some work to do is m. I need to change these to the same base. Tricky, tricky, tricky. I can change this very easily to base 5 as 5 to the negative 1. Oh, you're saying, yep, exactly. So now you've got the bases are the same. The exponents must be equal. It's a logic statement. So 2x equals negative 6. X equals negative 3. Well, welcome to the end of our video. Your homework, and it needs to be completed, will be on page in your workbook 127. And you can do 1, 2, 3, 4, 5, and 6. And what I suggest that you do is you do a couple out of 1, a couple out of 2, a couple out of 3, a couple out of 4, a couple out of 5, a couple out of 6. Go away for a while, come back, do a few more, make sure you're getting them right, and then you know you've got the understanding of what's going on here. If I turn on the back, oh, there's also 7, 8, 9, and 10. Haha, do those two. So in other words, this entire page, numbers 1 to 10, you need to be able to do. You'll notice that there's answers at the bottom of the sheet. All right, ladies and gentlemen, enjoy, and we'll see you soon.